Okay, can everyone see the slides?
Yes.
Okay, perfect. So I think let us wait for one more minute. I expect more students will join. Okay, let's start. So first of all, I'm sorry that I cannot teach. I cannot do the classroom teaching because of the COVID. I feel much better now, and some students send me email and ask me my health status. I feel much better now, and I'd like to do some test today or tomorrow to ensure that um, my status is negative, so that I can return to the classroom next Tuesday. But today, because of the safety issue, so can only discuss our lecture online. Yeah, but again, feel free to interrupt me in the Zoom. I'm happy to talk about any questions in the online lecture as well. So first of all, I want to remind everyone that our deal for homework 1 is this Friday. So from our office hours feedback, many students have already started, and at least a few students who came to my office hour, they're doing pretty well and only left a few things to do for the homework 1. That's really, really great. So if you haven't started homework 1 yet, or just start a little, so please hurry up, and also please take advantage of the office hours, especially tomorrow. There will be 5 hours office hour, but starting from 8 a.m. So please take advantage. Okay. So today we're going to talk about ensemble learning. So what does ensemble learning mean? So basically, you can will ensemble learning is a way to leverage an ensemble of learners. And later we'll talk about what kind of learners to use, right? And but basically, you can imagine we want to collect a set of classifiers or predictors, and we want to leverage them smartly, assemble them into a much more powerful classifier or predictor. That's the goal of the ensemble learning. So the two most important strategies in ensemble learning is called boosting and bagging, which are the major focus of our topic. So here's the outline. We're going to talk about ensemble learning. So first, we would like to give a formal introduction of the idea of boosting. We're going to give we're going to explain how the concept of boosting arised, and what's the formal definition of boosting, and what's the general framework of boosting, what's the intuitive idea. And then we're going to give a detailed introduction about AdaBoost, which we actually have mentioned a few times before. This is one of the most successful boosting algorithm, and now it's used in numerous like basic algorithm components, even in hardware. And we're going to talk about how to implement AdaBoost algorithm. And then we're going to talk about the bagging method, right? So you see that bagging methods actually are even simpler than the boosting type of methods. So and bagging methods apply to almost all kinds of learning algorithms, like decision trees, like neural networks, like linear regressors, and all kinds of stuffs. And and you see that by simply combine a set of decision trees or neural networks and take the average of their predictions, you can surprisingly get more stable and more accurate results. And we're going to explain why using the computational learning theory we have discussed or have previously discussed. Okay, what is boosting? So boosting is a general learning approach for constructing a strong learner using a collection of weak learners. Now here, in theory, it might need like possibly infinite number of weak learners, but this is just a theoretically meaningful, meaning that in a computational learning theory framework, you want to find a strong learner by assembling a bunch of weak learners to reach some good theoretical generalization error bound. You might need some like infinite number of weak learners in practice. However, we'll always use a finite number of weak learners as we like what we have discussed in a general boosting algorithm framework and AdaBoost. So how was the concept boosting invented, right? So historically, it was motivated by a theoretical question in pack learning. Right? So what's the definition of pack learning? Right? Probably approximate correct learning, right? We have discussed about it in last week, right? So let's do a quick refresh of our mind, right? Pack learning basically means, okay, if you want to learn something, you don't need too many examples, right? You just need a polynomial number of the examples. You can have some high probability to find a good hypothesis, meaning that this generalization error is less than some designated level, right? For arbitrary data distribution, to learn arbitrary target function in the concept family, right? So in the theoretical computational science, people want to ask, can I derive the strong learnability, namely pack learnability, through a set of weak learnability? So later we're going to talk about what do we mean by the weak learnability. But here I want to emphasize that although boosting was motivated by some theoretical questions, it turns out to be practically very, very useful. So it is the most popular way one of the most popular ways to create a strong learner using just a set of weak learners. The good thing is that those weak learners are usually very, very cheap to generate. Right? So you can imagine you can use a very limited resources, you can generate a bunch of weak learners. And now you have a very strong method to combine them together, to assemble them into a much more powerful classifier. So that's why it's very useful and very amazing in practice. Right? So boosting is a typical ensemble method that composes classifiers using other classifiers as building blocks, and boosting also has a stronger theoretical guarantees than other ensemble methods. That's very natural because it was originated from the computational theory questions, right? But here I want to emphasize that you can see that some theoretical motivations can still give us some kind of practically very, very useful algorithms. This is one example, right? Another example that we're going to discuss later in this semester is about support vector machines. So you can see that the development of the support vector machines is also driven by the computational learning theory. So we want to make the generalization error bound as small as possible. How can we do that? Then people find out, okay, we need to maximize margin, right? So when we maximize margin, it leads to the development of the so-called support vector machines. Okay. So here are a set of real-world applications where the boosting algorithms have been successfully used, like face detector, which we have mentioned quite a few times. Nowadays, we use like any camera, like in your cell phone, you take pictures, they can automatically bound the faces, right? So it is very fast and very accurate. So it is mainly implemented by AdaBoost, handwritten letter recognition, text classification, news tagging, information retrieval, DNA sequence analysis, and etc. So a lot of successful applications. So what's the formal setup for boosting, right? So although we're not gonna talk about too in depth about boosting theories, but here we want to give a little bit formal formulation of the boosting problem. So first, according to our discussion in the computational learning theory framework, we introduced the pack learning algorithms, right? So those pack learning algorithms is really worded as the so-called strong pack algorithms. So basically, assumes that okay, our algorithm is powerful, that for any data distribution over the instance space, right, and for every designated error level epsilon and designated confidence level delta, right, the learning algorithm only needs a polynomial many random examples. It can have a probability at least 1 minus delta, meaning that it has high probability to find a good hypothesis whose generalization error is no larger than the given error level epsilon. Right? So this type of algorithm is called strong pack algorithm. Of course, it is strong, right? It's very powerful. And on the other side, right, people also define another set of algorithm called a weak pack algorithm. So the weak pack algorithm, the definition is almost the same as the strong pack algorithm, except that we don't have such a strong requirement about the error level. So we now relax our need or our requirement of the error epsilon to be only to be bigger than half minus some small value of gamma. So gamma is bigger than 0, right? So basically you can imagine, okay, if I set gamma to be 0.01, then my error can be bigger than 0.49. Okay. So basically, the weak pack algorithm for any data distribution, for any confidence level delta, and it uses a polynomial many random examples with high chance to find a hypothesis whose error can be quite big, right? Can be close to half, right? So its error is still less than epsilon, but because epsilon is just a little bit less than 50%, right? So basically means this weak pack algorithm can quite efficiently find a strong, a weak classifier whose prediction error, whose generalization error is kind of close to 50%. That is called a weak pack algorithm. So any questions so far? is there everyone good with the two concepts we discussed here? Okay, yeah, it sounds good. So basically, the definition of weak pack algorithm and strong pack algorithm actually divide the capability of our learning algorithms. One is very, very strong. Right? For any error level, any confidence level, you only need a polynomial many training examples to find that hypothesis can be accurate, actually accurate, right, with high probability. But for weak pack algorithm, okay, it can guarantees to, with high probability, find a hypothesis or classifier. However, the error of this, the generalization error of this learned hypothesis is pretty bad. Right? It can be actually close to 50%. Of course, it's still less than 50%. Right? It's bigger than 50%. Then it's not. Then this classifier, this hypothesis, is not useful at all. Right? So then the theoretical question is, does weak learnability lead to strong learnability? Meaning that, can we start with some weak pack algorithm to derive some strong pack algorithm? Okay. So that's a very interesting theoretical question. Right? There are a lot of papers, numerous papers discussing about that. Right? So here is the history, brief history of the boosting algorithms, along with the development or the analysis and the research on this theoretical question. Right? When people try to answer this question, they need to propose some algorithm framework and then show that, okay, this framework can combine a set of weak learners and to derive a better learnability. And finally, you want to say, okay, if their combination or assembling algorithm can finally result in a strong pack algorithm. Right? So here's a brief history. So in 1989, Robert Shapiro, he's kind of pioneer in this research area, proposed the first probable boosting algorithm. So it's basically called weak learners 3 times on 3 modified distributions. It got slightly boosting accuracy and just apply it recursively. So it just has some like theoretical value, but doesn't have any practical value, right? And then Froome in 1990s proposed the optimal algorithm that boosts by majority, which is kind of similar to the idea we're going to discuss later today, right? And then in 1992, these 3 computer scientists experiments use boost and found they are limited practical value, right? And then the milestone and the breakthrough was made in 1995. Froome and Robert Shapiro introduced the so-called AdaBoost algorithm, which is the major focus on the boosting algorithm we're going to discuss. Right? So it shows the strong practical advantages over the previous boosting algorithm. Actually, it shows excellent performance and even better than many known strong classifiers. And after that, a huge number of papers and practical applications were proposed following AdaBoost. And these 2 computer scientists won the Godel Prize in 2003. The Godel Prize is actually the highest award in theoretical computer science. Okay, so here is the brief introduction of the boosting, the idea of the setting of the boosting algorithms and the motivation of that, and also the formulation of that. So next, we're gonna talk about more concrete things, right? Especially AdaBoost, right? How AdaBoost assemble a set of weak learners, weak classifiers into a very strong one, right? So we're gonna start with some intuition. We're gonna use some detailed concrete example to show the idea, and then we'll talk about the algorithm details, and finally we'll analyze why it works. and why it works so well. And also there's some typical behavior, and there are some open and seeing that, okay, the AdaBoost seems overfit the training data, but such kind of overfitting seems not harm the generalization performance. Right? This is actually an open problem, open question, and has yet been answered from the theoretical perspective. Okay, any questions so far? Yeah, feel free to interrupt me even in the Zoom environment. Everyone's good? Yep. Okay. So let us start with a toy example. So suppose here is the set of training examples we have, right? So in this rectangle domain, we have like we have 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we have 10 examples, positive and negative, 5 positive, 5 negative, right? So here we have weak learners, right? Our weak learner is either a horizontal line or a vertical line. Right? And initially, we will all examples as equally important. Right? So how does the boosting algorithm work, right? So in the first round, we're going to use the current examples to train a weak learner. Of course, the best weak learner on this data set, right? Suppose it turns out to be H1, which is the vertical line, right? And position here. Right? And although we say it's best, it doesn't mean that it can perfectly fit the trained data because it's a weak property, so it cannot perfectly fit the trained data, right? Actually, if we look at the H1's prediction on the training set, we found that there are 3 mistakes, right? This here, here, and here. So then we can see that the error is 0.3, right? Because there are 3 mistakenly classified examples out of like 10 examples in total. So the error is 0.3. Right? Oh, okay. So then what is the next step? For the next round, we're going to increase the importance of the examples with mistakes. And then downweight the examples that H1 got correctly. So basically means, okay, if for all the examples, H1 incorrectly predict these 3 positive examples, we're going to increase its weight, meaning that promote its importance. Meanwhile, we decrease the importance of the remaining examples which are correctly classified by H1. So if you use the size to indicate their importance, so you can see that the weights of these 3 examples get larger, and the weights of the remaining 7 examples get smaller. Right? The reason is that now that H1 has already been able to correctly classify those 7 examples, they are not viewed as that important in next round. Right? Instead, we want in the next round of learning procedure, the classifier will focus more on those examples that were misclassified in the previous round. So expect that in the next round, we can have a new hypothesis or new learner, which can correctly predict those examples, right? We can correct the mistakes made by the previous hypothesis. Right? That's the intuition, right? Why we would like to adjust the weight of the examples after each round. Okay. So that means at every round, we're going to maintain the set of sample weights we denoted by D of t, right? So we maintain 1 weight for each example. This weight indicates how much should the weak learner care about this example in learning the classifier. Okay? And here we also require the summation of the weights of all the examples is 1. So that means they are normalized. So now we have already obtained H1 in the first round. Based on those reweighted examples, suppose we get H2. Okay? And H2 is another vertical classifier where position is here. Right? Of course, because it is a weak classifier, we cannot guarantee that it can correctly predict all the examples, all the training examples, right? So if we look at the prediction made by H2 over the training examples, we still find 3 mistakes. However, this time, the error is not 0.3, instead, it's 0.21. I want to ask why. Any thought? Can you speak louder? I can't hear you. I'm trying to open the chat box. Yeah, I saw someone said, okay. I saw Jim said because the weights changed. Yeah. Any other supplement? Or you guys agree? Yeah, James is correct. Because the weights have already been changed. Remember, after first round, right, when we recompute the weights, right, when we readjust the weights of the examples, we have downweight those 3 negative examples. Why? Why we have downweighted those 3 examples after first?
Because the previous weak learner has already correctly classified those examples.
Yeah. Yes, exactly right. Remember that this is the H1, right? So H1, these 3 negative examples, I think it should be these 3 here. These 3 negative examples have already been correctly classified by H1, right? So their weights are decreased because they are not built as that important in next round of learning, because in next round of learning, we want the classifier or learner to focus more on the mistakes made by H1. Excuse me? Okay, so we know that, okay, these 3 examples have been downweighted. So now in the second round of learning, we got H2, right? And those 3 negative examples, unfortunately, were misclassified. So when we compute their error was decreased, is no longer 0.3, it's 0.21, right? But if you look at the misclassified examples by H1, these 3 positive examples, now they are all correctly classified by H2. Okay. So why not after round 2, the error is 0.21 rather than 0.3? Because while computing the error, we'll weight each example xi by its weight. Okay. So in general, what's the formula to compute the weighted error after each round of learning? So here is the formula. So after every round, we compute the weighted error over the whole training set, weighted training error in the whole training set as follows. So we subtract half by half times this summation over all the training examples. Each segment is the weight of the example I times the product of yi and h of xi. So yi is a ground truth label. It is either 1 or -1. And h of xi is the prediction made by the learned hypothesis, which is also either 1 or -1. if we look at the cases where we make a correct prediction or wrong prediction, for any particular example I, right? When our prediction is different from the ground truth, that means y is not equal to h of x, then we have this product yi h of xi to be -1. Right? So if here is -1, you got minus outside, minus becomes positive, you're essentially as a weight, right? As a sample weight, right? On the other hand, if your prediction is correct, meaning y is equal to the prediction, right? Then this product is positive, right? You both are either positive or negative. So when they multiply together, they always end up with 1, right? Then when this is 1 and the outside is minus, so you're essentially subtracting the sample weight. So we'll combine these two cases together. We can show that, right? This weighted error epsilon t is essentially just the summation of the weights of all these incorrectly predicted examples in the training set. Right? So as to y, we can derive epsilon t into this form. I will leave as an exercise for you. It will be, I think it will be a one homework question in our homework 2. Right? So any questions so far regarding the definition of this weighted error and why our weighted error can vary along with the running the training iterations or training runs? Everyone is good, right? Okay, let us continue. So after we got H2, right? We know some examples are correctly classified and some examples here, and here, unfortunately, are misclassified. Again, we're going to increase the importance of the mistakes and then downweight the examples that H2 got correctly. So we can keep doing that. Right? And then in round 3, we learn a third weight classifier, which is now a horizontal line. Right? And this time, we still got a 3 misclassified examples, right? Here, here, and here, right? And because the change of the sample weights, when we compute the weighted error following this formula, we got epsilon 3 to be 0.14, right? You can see that the weighted error kept decreasing, right? And the part of the reason is that, okay, all those 3 examples are downweighted twice in the first 2 rounding rounds, right? Okay, suppose our boosting algorithm stopped at this point, meaning that we have collected the 3 weight classifiers, like H1, H2, and H3. So at the final stage, we're going to combine all the 3 weight classifiers into one. So our final hypothesis, how do we combine them? We just do a linear combination. So we define our final hypothesis or final classifier as alpha1 times H1 plus alpha2 times H2 plus alpha3 times H3. So basically, if you throw any test example, test input X, say, for example, right? If you want to know what is the prediction of our final hypothesis, it is equivalent to first use H1 to make a prediction, and then weight this prediction by alpha1, right? And then use H2 to make a prediction, then weight this prediction by alpha2, and then use H3 to make a prediction with this prediction by alpha 3, and combine them together to get our final prediction. So we can think of those alpha values, alpha 1, alpha 2, and alpha 3, as the vote for each weak classifier. And of course, we need to specify how we assign alpha 1, alpha 2, and alpha 3 for those weak classifiers. Okay, so this is a simple illustrative example to showcase how the boosting algorithm runs in general. Okay? So here we give an outline of boosting algorithm. Suppose we're given a training set, which consists of m pairs of input and outputs, and each label of output yi is binary, which is either -1 or 1. Suppose we're gonna run big T rounds. Right? So for each running round, we're gonna construct a set of sample weights, D of T, over all the M training examples. And based on this weighted training examples or training set, we find a hypothesis H of T such that it has a small weighted error epsilon T. Okay? So once we have finished this big T rounds, we construct a final hypothesis by combining this big T weak learners or weak classifiers. So here's the general outline of the boosting algorithm. Any questions so far? Yeah, can you speak a little bit louder?
So I didn't get this. Can you please repeat once again? Sorry.
Repeat the algorithm again, or repeat what?
This one, this slide only.
Oh, this slide? Okay, this slide is just a basic summary of the toy example we have explained, right? And also it's a summary of the general boosting algorithm procedure. So suppose we have M training examples, where here we just assume we're doing binary classification, where each label is either -1 or 1, right? So the general boosting algorithm will run for big T iterations, right? For each iteration or each round, we first construct a set of sample weights over the training set. So meaning that for each training example, we're going to assign a weight. And of course, we need to ensure their summation to be 1. And based on those weighted training examples, we're going to learn a weak hypothesis H of T such that it has a small weighted error epsilon T. And then after these big T iterations are done, we're going to construct a final hypothesis by combining all the learned weak hypotheses H1, H2 to H big T. Does it make sense?
Thank you. Yes.
Any other question? Okay, good. So this framework or this outline is still far from being practically useful, right? Being practically useful, we need to specify these 2 steps, right? First, how do we construct the weights of the training examples, right? How do we set up the weights for every example? And the second question is, how do we construct a final hypothesis? Meaning, how do we combine the learned hypothesis at each training round, right? And assemble them into a final hypothesis, right? So in the previous discussion, we just mentioned that, okay, we're gonna do a linear combination of those linear classifiers, but how do we assign the votes, right? Alpha 1, alpha 2 to alpha big T here. Right? And different instantiation of these 2 steps lead to different boosting algorithms. So here we're gonna concentrate on the AdaBoost. Okay. So let's first take a look at how AdaBoost construct the sample weights D of T. So suppose we have m examples, dt is the set of weights over those m examples. So we denote dt1, we denote by dt1 the weight for example 1, dt2 the weight for the example 2, until dtm the weight for the example m, the last example, right? So at every iteration, the weak learner looks for hypothesis HT that emphasize examples that have a higher weight dt, right? That's the idea of boosting, right? So initially, AdaBoost uses the uniform distribution over all examples. That means we set the weight for each example to be equal, which is simply 1 over m, right? Because we have m examples in total. Okay? And then after t rounds, right, after small t iterations, what we have is that, okay, we have current d of t, and also we have the hypothesis d of t, h of t that was learned, right? We have also computed the weighted error of that hypothesis on the training data, right? And then we want from the t+1 iteration, we can find a hypothesis so that examples that were incorrectly predicted in the previous round can now be correctly predicted, right, by the new hypothesis. How can we do that? We're going to increase the importance of the misclassified examples by h of t, right, learned by the previous round, and then decrease the importance of those who have already been correctly classified. Right? And how can we do that? Right? So AdaBoost just multiply the weight at the previous iteration by a factor. Right? So for a particular example I, right? So dti is the example, is the weight of example I at iteration t, right? So if we want to obtain the weight at iteration t+1, right? So we just look at if the prediction made by h of t, the learned hypothesis at iteration t, is correct or not, right? If it is correct, right, meaning the label yi is the same as the prediction made by h of t, right, over xi, then we multiply the previous weight by this fraction, which is e to the power of minus alpha t, right? The alpha t is positive number. On the other hand, if the prediction is wrong, yi is not equal to h of t xi, then we multiply the previous weight by e to the power of alpha t. Okay. So these two cases can be unified into one formula, right? So basically, we multiply the previous weight dti by e to the power of minus alpha t times yi times ht of xi. So I want to ask why we can unify the two cases into one formula.
Because
Yeah, feel free to say that. It's yeah.
If yi equal to hi, then it will be 1.
Mm-hmm.
If we multiply them, if it is not, then it will be minus 1.
Yeah. So any other different idea or different thought? Okay, I assume you have the same idea, right?
yes.
Yeah, exactly, right? So actually, the product of the label and the prediction is a good indicator on whether you make a correct prediction or not, right? If your prediction is correct, then this product is always 1, right? When that means you're essentially multiply e to the power of minus alpha t, because this guy is 1, right? On the other hand, if your prediction is wrong, then this product is always minus 1. So minus 1, minus 1. So you end up with e to the power of alpha t, right? So it's a nice and concise formula So we don't need to implement an if-else statement in your implementation. Right? So, but if you look at these two cases, we can see how AdaBoost fulfills our design idea. Right? So first, if our prediction is correct, we multiply the previous weight by e to the power minus alpha t, right? Because alpha t is bigger than 0. Right? So e to the power of minus alpha t essentially is a scalar between 0 and 1. So essentially, demote the correctly predicted examples. Why? Because it kind of decrease the scale, right? Because you multiply the previous weight by a number less than 1. Right? On the other hand, if your prediction is wrong, right? So you multiply you multiply the previous weight by e to the power of alpha t. So this guy is bigger than 1. So actually, you amplify the weight and you promote the incorrectly predicted examples. So that's the strategy used by AdaBoost. Someone asked, do we have other methods to update the sample weights? The answer is, of course, yes. Right? But here, we just give the popular AdaBoost specification. Right? So now, let us look at ZT. Right? So why do we introduce a ZT in the denominator? Right? The reason is that we want the summation of all the weights over the training examples to be 1. Right? So that must be normalized to 1. So ZT here is a normalization constant. It is to ensure that the weights dt plus 1 adds up to 1. Right? So how do you compute ZT? Any thought?
Add up all the weights.
Yeah, exactly. Right. So if you want to compute this normalization constant, right, don't be scared, because some students, previous years, past years, some students ask, we're concerned about that. Actually, it's not. You don't need to concern about that. So you can first compute the unnormalized weight, meaning that you only compute the numerator, right? DTI multiplying with the factor, right? For every example. Then you just add them together, you get ZT. Because when you divide by every unnormalized weight by this ZT, we add them. When you add up them together, it will ensure you to get 1. Right? This is how you get ZT. And don't forget that if you don't correctly compute ZT in your AdaBoost implementation, you will find the algorithm's behavior is very bizarre. Okay, the final thing we need to be clear is that how do we compute alpha t? Right? So alpha t is computed as follows. Of course, this is a AdaBoost special definition about alpha t. If you have other variants of the boosting algorithm, they might have a different definition of alpha t. But here we just show alpha t, show the definition from AdaBoost. So alpha t is computed half logarithm of 1 minus epsilon t over epsilon t. So epsilon t is the weighted error. Because the weighted error epsilon t is less than half, then 1 minus epsilon t is bigger than half, right? So the fraction here, like 1 minus epsilon t over epsilon t, will be bigger than 1. So alpha t will be a positive. But here, alpha t is not only used to update or recompute the sample weights. It is also used as the final vote when we assemble those weak learners into the final classifier. I remember in our discussion a minute ago, we said that the final hypothesis is alpha 1 times H1 plus alpha 2 times H2 plus alpha 3, H3, and blah, 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 right? So those alpha T also serve as the votes of each learned weight classifiers moving to the final prediction. So now we have specified the two. We have specified how we construct the data distribution in each learning iteration or each learning run. Right? So before we proceed, the step to construct the final hypothesis with the learned hypothesis in iteration 1 to big T. So any questions so far? So is everyone comfortable? Okay, that's great. Okay. So now let us proceed to the final hypothesis construction step. Right? So after we finish the big T iterations, we have collected the T weight classifiers, H1, H2 to H big T. And also we have computed big T values of alpha T, right? Alpha 1, alpha 2 to alpha big T, right? Each alpha corresponds to one weight classifier. And here we assume that each weight classifier takes an example X and produces a label, binary label, which is either -1 or 1. Right? Then we define the final hypothesis as just a linear combination of every weight classifier weighted by alpha t's. And then we take the sign of that. So now I want to ask, what does this final hypothesis prediction mean? Like, okay, for any test input X, right? If I want to get my final prediction, how can I do that? According to this formula, we're gonna throw X into every weak classifier, H1, H2 to H big T, and make prediction, then multiply with alpha T. Add them together, then take the sign. So I want to ask for your understanding of this assembling rule.
We are taking a weighted majority.
Yes, exactly, right? So because each weight classifier produces either 1 or -1, right? So you can imagine each prediction is voted by the corresponding alpha T, right? We'll add them together. We can will like, okay, I got this much vote for the positive prediction, which is 1, right? And I have this much vote for the total vote for the negative prediction. They compete each other, right? If the positive prediction, the positive 1 label wins, that means this whole summation will be positive. Then the sign will give you 1. On the other hand, if the total vote of the negative prediction is bigger, wins over the total vote for the positive prediction, then this summation will be negative, right? Then the sign will be a -1. So essentially, it fulfills the weighted vote of the prediction made by all the weight classifiers. Does it make sense? Okay. Now, let us look at the full algorithm of AdaBoost. Again, we assume we are given a training set of m examples, x1, y1 to xm, ym, where each label is either -1 or 1, right? So we need to specify a hyperparameter t. The t is actually the number of iterations or number of training rounds, right? So in the very first step, we're going to initialize the weight of each example to be equal, namely 1 over m. M is the size of training data. Then we go through big T iterations. For each training iteration, we find a classifier h of t, the weight classifier h of t, whose weighted error is better than chance, meaning that it's bigger than the error is less than half. Right? Then we compute the vote for this weight classifier following this formula. Alpha t equals to half logarithm of the ratio between 1 minus the weighted error epsilon t and epsilon t. Then we use alpha t to update the weight of every training example following this formula we have just discussed. Right? Then we finish the training iteration t, right? Then we'll proceed the training iteration t plus 1, and we'll do the same 3 steps. Repeat these steps until all the big T iterations are done. And then finally, we return the final hypothesis, which is essentially a linear combination of all the weak learners through these big T iterations, where the prediction for arbitrary input is simply a weighted vote of the prediction made by every weak learner. Right? The vote is computed by the alpha t in each iteration. Okay, any question regarding the algorithm details?
How to
What
know,
if you,
how to know where to terminate, like how many number of iteration we should go for?
Oh, that's a good question. We don't know. In the practice, you need to adjust and select big T. It's kind of like it's kind of like application driven. It's problem specific. It's not like I tell you T is 1 or T is 10 or T is 100 is enough.
if you get an error of 0, isn't that going to make your alpha like undefined? And then how do you handle that?
You mean epsilon T is 0?
Yes.
If epsilon T is 0, of course you have to stop, but usually it's highly unlikely because this is a weak classifier. So we don't assume that your weak classifier can correctly classify all the examples every time.
Gotcha. Okay, thank you.
Yeah. But I wouldn't say, okay, this is highly impossible, because there could be some cases, for example, it's so easy, like even a weak classifier can give 0 training error. In that case, you have to stop, right? Because there's no need to proceed anymore.
Gotcha. Okay, thanks.
Any other question? Okay. So now we go back to the toy example, right? So in the toy example, what I'm showing you that after 3 rounds of learning, we collected 3 weight classifiers, 2 vertical lines, the 1 horizontal classifier. They have their votes alpha 1, alpha 2, and alpha 3, right? So now if we combine them together, right, using alpha 1, alpha 2, alpha 3, and then we really look at the classification boundary, we can now 100% accurately predict all the training set, okay? And this is a classification boundary, which is highly nonlinear. Okay? So this actually demonstrates the power of the boosting. So basically, for each weight classifier, they are very simple, intuitive. The boundary is just simple horizontal line or vertical line, right? However, when you combine them together, even simple linear combination the boundary, the classification boundary becomes much more complicated. And as the result, as the outcome, they can 100% fit the trained data now. So in practice, what is the most often used weak classifiers for boosting? Actually, it is the classifiers we have just discussed, like decision trees. And of course, we don't use a very large, very tall, or very deep trees. Instead, as you will see in our homework 2, which is going to release in the next week, the weak learners using AdaBoost is often the so-called decision stumps, meaning that I only expand the tree for one level, meaning that every time I only pick up one attribute to split on the data set, and then I stop the tree growing. So this one level decision tree is often used as a weak learner to construct to construct the strong classifiers with the AdaBoost algorithm. So I think before you are asked to implement the AdaBoost algorithm with decision trees, I want to give some more hint of the implementation in case that you're confused at some steps, right? So the major things or major problem some students might have met or feel confused is how to compute the information gain for the weighted examples, right? So as we discussed, a critical step in the boosting is to reweight the training examples after each training iteration, right? So that means when you implement your weak learners, right, like one level decision tree or decision stump, you need to deal with weighted training examples, use them to compute the information gain of each attribute. Right? The question is, how can we compute them? Right? Actually, the solution, we have discussed about the solution. The idea is to will those examples as fraction examples. So this is exactly the same as we deal with missing attributes and with fractional examples to infer all possible choices of attribute values. Let us give a quick review of that. Suppose here are the 5 examples, right, we want to deal with, right? And this is our training set. And we're going to use a decision tree. We're going to train a shallow decision tree as our weak learner. Right? In the very first round of the AdaBoost, right? Because all the 5 examples are equally weighted, meaning that their weight is 1 over 5. Right? So if we want to compute or learn a decision tree, right, we need to compute the information gain for each attribute, all log, temperature, humidity, and wind. Right? And to compute that, we need to compute the entropy, right? So the entropy, we need P positive and P negative. So I want to ask, what is P positive and what is P negative? How do we compute them?
Previously, when we were computing the probabilities, I think we just assumed that every data sample has a weight of 1. And then say if, in this case, there are 3 positive samples out of 5. So you just calculate it as 3 by 5. But then when you have different weights for each of these samples, you just sum up the weights of all positive examples and divide it by the sum of weights of all samples to get the probability of the positive class. And so on for the other classes.
Exactly. Yes. Yes. Exactly. Right. So we just sum up all the weights of the positive examples, which is 1/5, 1/5, 1/5, right? And then divided by the total weights, the summation of total weights over all the examples, which is 1, right? Which is 3/5, which is p positive. And similarly, you can compute p negative. You sum up the weights of all the negative examples, then divided by the summation of all the weights, which is simply 1, right? So it's 2/5. Then you can compute entropy accordingly, right? And similarly, when you use any attribute to split onto a data set into several subsets, and then you compute the corresponding p positive, p negative, compute entropy. Now you compute the weighted, you compute the weighted summation of those entropy of the splitted subsets and subtract the total entropy, you get the information gain. Okay. Now suppose we proceed to round 2, okay? And after round 1, and due to some examples are correctly classified, some examples misclassified, then the weights of the examples have been adjusted, right? So they're not equally weighted anymore. So for example, the example 1, negative example was weighted as 2/8. Second example, 1/8, 3/3, 1/8, 4, 3/8, 5, 1/8. Right? Now, if we want to compute p positive, we just add up the weights for all the positive examples, which are 1/8, 3/8, 1/8, which is 5/8. Right? And similarly, we compute p negative 3/8, we compute entropy accordingly. Right? So just will them as fraction examples and then compute them as you deal with fraction examples in your homework 1. Then you will learn your shallow decision trees according to those weighted examples. So this is not hard, and I don't think you will feel difficult in that. But if you miss the details here, you don't will them as fraction examples, you ignore the weights of the training examples, then the learning behavior of your AdaBoost won't be right. You will feel very weird. For example, some other students' implementation for AdaBoost, you cannot observe the training error keeps decreasing to be a very small level, while the test error also decreasing and convergence to a very good level. And you might see like very weird situations. Okay, any questions so far? Is everyone comfortable? Okay, perfect. So here I want to present some theoretical results about the AdaBoost. Again, this is not ask you to show this proof, show this theorem, and also you are not required to master the proof of this theorem, although we have given a link to this proof in our course website after the lecture. If you're interested, you can take a look. The technique is not hard. It's just some basic calculus and probability inequalities, but it's very interesting. But here we want to emphasize the power of this AdaBoost algorithm in terms of the reducing the training error. So here's our theorem. Suppose we can run AdaBoost for big T iterations, big T rounds. So we denote the weighted error of each iteration small t by epsilon t, and we represent epsilon t by half subtracted by gamma t. Sorry. So here we represent epsilon t in this way is just to emphasize that each iteration we actually have a weak learner, right? And weak learner, the error is actually close to 50% chance, like you run plus a quant, right? So this gamma t actually is quite small. if all those gamma t's, I mean, across the big T iterations, have some common lower bound, and this lower bound is bigger than 0, meaning that there is some gamma which is bigger than 0 and less than or equal to gamma t for all the t, then we claim that the training error or the empirical error of the final hypothesis. Remember, the final hypothesis is a linear combination of all the weak learners' hypotheses in the big T iterations. This training error will be upper bounded by e to the power of minus 2 gamma squared times big T. Okay. So here, I will emphasize, we assume a non-zero lower bound for all the T. This is may not always be the case in practice, right? So what does the conclusion mean, right? The conclusion, let me say it again, right? So the training error is upper bounded by e to the power of minus 2 gamma squared t. So what can we observe from this conclusion?
As you consider more and more weak learners, your error of the combined hypothesis reduces.
Yes. And it reduces very, very fast, right? So remember, it's e to the power of some constant minus constant times t, right? So when you increase t, the training error actually drops exponentially, right? So it's very, very fast. So when you run more and more iterations, meaning that you ask for more and more weak learners, right? Then the combined the weak learners, the assembled weak learners into this final hypothesis, this training error decreases exponentially fast, along with the number of weak learners request. So you can see that the AdaBoost can fast fit to the trained data very well. Okay. That's the property of the AdaBoost. Right? Although every time we just learn weak learner, but if we can assemble this weak learner, we can train them in right order and assembly them in a smart way, and their combined their combination can make the training error, can fit the training data super well. Right? You don't need many weak learners. You can perfectly fit the training data. This proof is not hard. If you're interested, you can take a look at that as we just mentioned. But here, I want to emphasize this series is on the assumption that your gamma, you have a common non-zero lower bound for the gamma t. Right? So in practice, it might not be always the case. So as you'll see in your homework assignments, although the theory said, okay, the training error can fastly reduce to be 0, right? But in the real data set we provide to you, you see that the training error won't directly go to 0. Right? It will arrive at a very small error, a small level, but it won't give you 0 training error. That doesn't mean the theory is violated. It just means it doesn't satisfy the precondition of theory, meaning that you have some common lower bound gamma here. So any questions so far? Okay. So a typical behavior of the AdaBoost training is like this, right? The training error of the combined classifiers decays exponential fast, right? If the errors of weak classifiers are strictly better than chance, right? What you can often observe is like this. Right? However, if you look at the individual classifier, meaning that each weak learner, right? With more and more iterations, the individual classifiers, their weighted error essentially tends to increase. That's a very interesting phenomenon, but it's also reasonable because you can imagine in the later stage of the training, right? Those hard to classify examples, those difficult examples, because they are often misclassified by the previous learners or classifiers, right? Their weights becomes larger and larger, right? And so in a subsequent learning procedure, those weak learners have to deal with those hard examples in the first priority. So it is less likely they're gonna correctly classify it as well. And because their weights are keep increasing, so you can imagine their weighted error turns out to be bigger and bigger. Right? That's often observed in the practice. And those discussions about the training error. Then what about test error? So from the previous discussion, right, we always claim that the overfitting is not good, meaning that if you have a zero training error or training error close to zero, that's a bad sign. That means during the training iterations, at some stage, your generalization error, meaning your test error, start to increase, right? So we don't want our training error to be so small. We want to pick up at some turning point to stop the training so that we can achieve the best test error, right? So, however, this observation usually doesn't fit the behavior of AdaBoost, right? Our boosting algorithm. So this is a typical observation for the AdaBoost algorithm. So you can see that along with more and more iterations, meaning that along with more and more weak learners, your training error keep going down until you reach zero training error. However, the test error doesn't increase as well. So keep decreasing until become stable at some level. This is a strange observation, right? The test error may decrease even after training error has hit zero. Why? This is an interesting question, right? This is still an open question, right? There are many possible explanations, but has yet a kind of like a golden answer on that. Like everyone appreciate that, right? So, but has some discussion explanation in Shapiro and his co-author's paper in 1997. Okay? But please keep in mind this kind of interesting behavior of the boosting algorithm. Okay, to summarize AdaBoost, right? What is good about AdaBoost? It's simple, fast, and only need one additional parameter to tune. That is how many iterations you want to run, and how many weak learners you want to call, right? And you can apply AdaBoost with any weak learning algorithm, although the most popular weak learning algorithm is the decision stump, namely one-level decision tree algorithm. So what are the problems? What are shortcomings, right? The performance, unfortunately, often depends on the data set, on also the choice of weak learners. Right? If your weak learners are not appropriate, meaning that if it is too complex, it can fail. If it is too weak, it can fail as well, like your weak learners. If occasionally even worse than random classifiers, meaning 50% chance, then it can fail. Right? Empirical evidence shows that if you use decision stumps as the weak learners, then the ADA boosting seems to perform best. Right? If you have only a small number of features, like if you don't have like tens of thousands features, if you use one level decision trees named decision stump as a weak learners and train and run AdaBoost, it tends to give the best productive performance. Okay, I think we can stop here, and we have finished up the boosting learning topic. Next Tuesday, we're going to talk about another type of ensemble learning approach. It's called bagging. Okay, thanks.
Professor, I had a quick question.
Yeah.
On slide 8, I was a little confused by the definition of
slide?
Slide 8.
Slide 8. Slide 68. Or
slide 8. Way towards the top.
this one?
Sorry, 8. So like right in the beginning.
Right at the beginning.
Yeah, 8.
Oh, okay. Let me find out. Slide 8. Here?
Yeah. So for that error in the weak pack algorithm, I was a little confused, and it kind of contradicted the rest of the lecture, which seemed to indicate that the error should be slightly less than chance. So or slightly better than chance, or no, the error should be slightly less than chance, so less than 50%. Should that be I'm not understanding that greater than or equal to sign.
So yeah. So epsilon here, epsilon is the level, right? So you can imagine gamma to be a very small value, like 0.01. So like I can set, let us just count, right? If I set gamma to be 0.01, then half minus 0.01 is 0.49, right? So that means my epsilon can be bigger than 0.49, say 0.495.
But it could also be like 1, right?
What?
It could also be like 1, right?
Epsilon. If epsilon is just 1, then it's not meaningful.
Oh, so it's in between 0.5 and like
in between, like some 0.495 and 0.5, and then I require, and my algorithm find a hypothesis which is still error less than epsilon. I mean, it's still less than 5, less than 0.5. But however, this epsilon is quite close to 0.5.
Okay, so epsilon is also capped by 0.5, so it can't be bigger than 0.5.
Yeah.
Okay, gotcha. That makes sense.
That's the practical requirement. Otherwise, you can imagine if you only set up epsilon to be bigger than 0.5, then that's not meaningful.
Right. That would be a good weak learner. It'd be worse than chance, right?
Yeah, it's worse than chance. Now, worse than chance, we don't will as a meaningful learner. Yeah.
Right. Okay. And then is that this also assumes like binomial, like 2 outcomes only, so it's predicting.
Yeah.
Only.
Yeah.
Okay, gotcha.
Those are all about a binary classification problem.
Gotcha. Okay, awesome. Thank you so much. I appreciate that.
Okay, no problem. Okay.
I hope you feel better. And
thank you. I indeed feel better. Yeah.
Great. Okay. Have a good one. Bye.
Yeah.